Okay, today's class is about the two basic topics. One is biological half-life and volume of distribution. We will start now our pure pharmacokinetic portion. Before this, you people understand regarding the some data, its interpretation, its graphical representation, there are some calculations, and in this case, we will divide this portion into different compartments. For the sake of compartment, we will discuss this into one compartment, and this one compartment will be divided into one compartment IV injection, oral tablet, IV infusion. Where we use the word one compartment, for the sake of linear pharmacokinetics, we will make some assumptions. We will assume that there is no metabolism of the drug. You will have to write these points. There are the basically 4 or 5 points which we will have to assume first. Then all the formulas and the calculations which we learn today will considered correct. One is there is no metabolite. Other is drug follows passive diffusion. You people know passive diffusion means it's concentration dependent diffusion. And the basic phenomena of this type of diffusion is basically change of the concentration from higher to lower. Second assumption is drug follows the passive diffusion. Third is elimination of the drug is only from the urinary tract. Only renal clearance is possible. Other clearances will be considered as fixed. And the drug is given by IV injection in case of IV injection, and given the oral tablet in case of IV infusion. 4 assumptions. Drug is given by IV injection. Drug is following passive diffusion. There is no any metabolism, and elimination is only by the renal clearance. There is no other way of the elimination of the drug. These 4 assumptions will give us the correct idea of these concepts of the biological half-life and also the volume of distribution. In case of biological half-life, and another is drug is following first order kinetics. Yes, the other assumption is drug is following first order rate kinetics. 5 assumptions, and by fixing all these, we will calculate the half-life of the drug. And half-life, first we'll define the half-life. Half-life is actually a time in which half of the drug is eliminated from the body. It's elimination half-life. If we discuss about the absorption half-life, then we will say it's a time at which half of the drug absorbed from the body. Absorb means drug coming from the GI system toward the circulatory system, systemic circulation. And distribution half-life is basically half of the drug distributed from the one compart to the other compart will be distribution half-life. It means we can divide these segments: absorption half-life, elimination half-life, and distribution half-life, even metabolic half-life. When the half of the drug, the time at which half of the drug metabolite will be called the metabolic half-life. How can we calculate the half-life? Half-life can be calculated by using the 2 different methods. One is from data, and other is from graph. In case of data, when we clear the concept of the first order and the zero order kinetics, we write the formula of half-life. The formula was T half was equal to 0.693 over K. K is actual elimination rate constant. Then we will write the T half. Okay, if I change this word T half 0.693 over Km, it means its metabolic half-life. Okay, if I change the word this T half is equal to 0.693 over Ka, its absorption half-life. And I change the word Kd, it means I am discussing about the distribution half-life. Okay, how this equation comes, we already know by the simple way. When we discuss the concentration, unknown concentration measurement formula, Cp is equal to Cp naught E minus Kt. This is the formula for first order kinetics, one compartment model. Cp is equal to Cp naught E minus Kt. If when we discuss two compartment, we will divide this Cp naught. It's this K1. This K1 will be K12, K21. I have already told you in the different diagrams. And in case of first order kinetics and one compartment model, we have the Cp is equal to Cp naught E minus Kt. And our target is to calculate the time at which half of the drug eliminated. So what we will do, we will check this time, then half of the drug is eliminated, we will say T half is T half, and this Cp naught will be equal to 100%, and now this Cp is it's 50%. The time at which initial plasma convert into half, elimination half-life. Then we will assume that we are taking the value Cp is equal to 0.5 Cp naught. When we write this 0.5 Cp naught, this will equal to Cp naught E minus Kt, and these Cp naught will be cancelled. K means 0.693 over T half, and this time this is 0.5, and we will check the half-life concentration by taking the natural log of the by taking the ln of these two, and we will get by taking the ln, we will write only minus Kt here. Minus Kt. When we take the ln will be cancelled. 0.693 minus Kt half, and T half will be minus cancel 0.693 over K. I have already told you when discuss our first order kinetics concept. Same calculations we can do by using the ln C2, ln C naught is equal to ln C is equal to ln C naught minus Kt. We have already proven that. Means if there is a question, convert this equation into this. For example, there may be two other concepts. Convert this ln C naught, ln C is equal to ln C naught minus Kt into T half is equal to 0.693 over K. Same case, please convert Cp is equal to Cp naught E minus Kt into T half 0.693 over K. Same case, log C naught minus Kt over 2.303 into T half 0.693 over K. I have written the three different conditions, but the meaning of all these conditions are same. Either we will solve this one, this way, and the last one. In the last case, I just apply the log and divide the minus Kt value with the 2.303, which is the factor for the equalization of the ln and the log. Then what we will do, we can also convert this into this equation to this equation to this. Why we are converting these equations? Because we have assumed that our drug is following first order kinetics, and this equation is the first order equation. And when we convert this for the half-life, then we will assume that T half is equal to 0.693 over K. This is our data method. Data method can be applied by converting the first order kinetics equation into T half is equal to 0.693 over K. Okay, what about the K? This K is our called rate constant. Rate constant may be elimination rate constant, absorption rate constant, or the distribution rate constant. When we construct a graph, three types of the graph. For example, we have a x-axis and y-axis have the amount of drug in milligram. Here is log of drug in milligram. Here is ln of drug amount in milligram. I have changed the y-axis. One is simple values, rectilinear. Other is log values, semi-log. Other is natural log values. Okay, data will show us this type of graph, values, because it's first order, and rectilinear shows us the parabolic status. In case of logarithm, it's straight line, and in case of semi-log, it will also, semi-log, also both semi-log, but we are taking the log value here, and we are taking the natural log value here. Both will give us the straight line. Okay, what will be the K? In this K, K will be the slope, but this slope is ln C2 minus ln C1 over T2 minus T1. But this case, in case of K is slope, but divide with the 2.303. First of all, we will calculate the slope with the log. For example, log C2 minus log C1 over T2 minus T1 into 2.303. What we are discussing? We are discussing this. If we extrapolate it, this value is Cp naught. Okay, when we extrapolate it, this value will be Cp naught. The Cp naught value will be, in case of logarithm and the natural logarithm, we will take these values and we will write here Cp naught. And if we know the concentration, half-life of the drug, then we can measure the concentration of drug at every time. For example, we want to know the concentration of drug at 4 hours. And the half-life of the drug is also 4 hours. Then we will write minus 0.693 over T half means 4, 4 cancel, and now Cp naught, it's initial concentration of drug in plasma. It can be calculated by dividing the dose, initial dose, with the volume of distribution, Vd. This is called Cp naught, without constructing a graph. If you know the dose of the drug and know the volume of distribution of drug, when we divide this dose with the volume of distribution, we will get Cp naught, initial plasma concentration. That concentration can be calculated by two ways. One is by graph. Just extrapolate it and coincide it on the y-axis. We will get the Cp naught. And the other is x naught over Vd. X naught is actual dose. For example, we are giving a drug to the patient which dose is 100 milligram and Vd of the drug is 5 liter. Then we will divide 100 with the 5. Answer is 20. Then our Cp naught is 20 milligram per liter. Units will be same as the units of the dose and the volume of distribution. Okay, when we calculate this Cp naught, K can be calculated by the half-life. T is the factor which we want to measure. The time where we want to measure the concentration, we can get the plasma concentration at every time. This equation is for IV injection. One compartment, no metabolism, passive diffusion, clearance through renal, first order kinetics, and drug is given through IV injection. After 5 assumptions, we can assume that this equation is perfect for the calculation of unknown concentration. And this equation can convert into the half-life area. We can calculate the half-life by just converting this equation to the half-life mode. Okay, in the case of when we assume that graph, okay, second part is graph. In case of graph, we will construct semi-log graph. Why we are constructing the semi-log graph? Because we have assumed at the first stage the data is first order kinetics. Drug is following first order kinetic profile. So we will construct a semi-log graph and we will get the straight line. And this straight line will give us a concept of half-life. For example, we have a scale 0, 2, 4, 6, 8, 10 hours. It's time. And we have a scale of the concentrations. Start with the 1, okay. Next is 10, next is 100. Is it? Log scale, semi-log graph. Then we will take, this is our concentration. This might be in microgram per ml. We will take a 1 point, it's 10 and it's half, it's 5. Okay, extrapolate it toward the straight line and then take the difference at x-axis, that is t half. Once again, we will construct a graph first. After getting the straight line, we will assume the two exact half values. For example, we are taking the value 20, the point 20 having the concentration 20. Then we will take the other point which is 10, because we are discussing with the half. Half means 20 to minus 10 is 10, half. Then we will assume that the time difference will be called t half, half-life. If we construct this graph for the elimination line, because this is only the elimination line, IV injection. But in case of distribution line, in case of absorption line, these values of the half-life will be considered absorption half-life or the distribution half-life. In this case, what we will do, we will take the two exact half concentrations. Here is 10, then I got 5. 10 and 5 having these 2 points, and their difference on the x-axis will be half-life, because half-life is a time and time is on our independent variable and time is on x-axis, time is on the input area. Then we will take the difference of the two exact half points, and this difference will give us the concept of the half-life. For example, I take the point 50. Okay, now I will search where is 25 or where is 100, because half of the 100 is 50, half of the 50 is 25. Then I will have to take exact two points which have the same concept of same difference of the half. Then we will assume, okay, it's 50, then there is say 100, and these 2 points we will get the difference of the time. This time will be half-life by graph. We are discussing how can we check the biological half-life. We can check biological half-life by 2 ways, by data and by graph. In case of data, we have a simple equation 0.693 over K, because we are fixing the parameters of drug. Drug is following first order kinetics. It means T half is equal to 0.693 over K. But in case of graph, we will construct a graph and take the exact 2 values. And after getting the 2 exact values, we will take the difference of the time that points, and then the difference will give us the idea of the half-life. Okay, but what's the units of the half-life? Unit of half-life is, because we know in case of rate constant per hour, rate constant unit was per hour. And when we write the units of 0.693 over per hour, it means when it will move toward the nominator, the units will be hours, minutes, seconds, days, the unit of time, because we are discussing with the time at which half of the drug eliminated is called the half-life. Okay, we will take an example and then we will clear our concept how the half-life is differ. Metabolic half-life are different, and absorption half-life is different, elimination half-life is different. For example, we have a drug its dose is 250 milligram and its dose excretion through urine is 125 milligram. And we are considering that there are the two metabolites of the drug, because now we are getting the concept of different types of the half-life. We have understand the ways of calculation of half-life. Now other is, how can we assume that metabolic half-life is different from the absorption half-life, and absorption half-life is different from the elimination half-life? Now we are taking some example. Dose excretion from urine is 125 milligram. Dose getting metabolized 75 milligram. And metabolite means M1. There are two metabolites of drug. Then its metabolite M2 25 milligram or 50 milligram. Okay. And half-life of the drug is 4 hours. First of all, we will get the concept of, here is Ku, elimination rate constant. Here is Km1 and then Km2. And its whole rate constant is K is equal to Ku plus Km1 plus Km2. Are you getting my point? There are different rates of the drug movement. First movement is we are discussing the amount of drug which is getting clear from the urine. We will say Ku, rate. And the other is Km1. Metabolic rate means getting the metabolites of the drug, stage 1. And another metabolite which is Km2. First of all, we will calculate these Ku, Km1, K2, Km2. And then we can also write this equation. T half is equal to T half elimination plus T half metabolic 1 plus T half metabolic 2. It's a combined name of the half-life, just like the rate. We can use the word for the whole scenario. Okay, in case of Ku, when we can calculate, it's 0.693 over T half. T half is 4R. It's overall K, 0.693 over 4. We will get answer. Then when we use Ku, we have 0.693 over 4, and we are getting this, it's almost 25%, 50%. And we will multiply with the 0.5. Same case, when we discuss this one and this one, these are the another portion of the 250, 75.07, and in case of 50.05, and we will get these rate constant, different rate constants, and we will combine it first and then make the cumulative rate constant, which is elimination rate constant. And same case, we will get the different half-lives: distribution half-life, metabolic 1 half-life, say elimination half-life. You will solve this equation, solve this formula. Okay, another is, when we take the concentration of the half-life. Why we are using this half-life? We are using the half-life, the parameter of half-life, which will be applicable for the calculation of some parameters. For example, dose adjustment, for example, for the sake of bioavailability studies, and we can check the function of the body. And the question is, if we want to make some study from the biological point of view, from the animals, from the human being, and how many samples or how much time we will have to apply to taking the blood from the human being. For example, you people are the part of the study of bioequivalence, and we want to draw some blood samples from you, and then we want to, first of all, as a pharmacist, as a investigator, we will have to check the time frame for how long I will take the blood sample, either from the animals or from the human being. In case of animals or the human being, there is some parameter. If we are taking the data from blood samples, then our need is T is equal to 4.32 half-life. We are now discussing the application of half-life. For example, you have given a target to take a sample from the patient to analyze the pharmacokinetic profile of drug. Your question is, how much volume of the blood I will take? Other is, how much time how many samples I will get from the patient, and this study will continue for how long? The answer is, we will check the half-life of the drug first. If the half-life of the drug is 1 hour, then we will put the value T half is here 1. 4.32 into 1 is 4.32 hours. For example, the drug which you are discussing for the pharmacokinetic profile is having the half-life 1 hour. We will take the blood samples at least at that time for the 4.32 hours. In case of drug having the half-life 2 hours, then we will apply this 2 with the 4.32. Our answer will be time needed 4.32 into 2, that is 6.84 hours. Means the drug, first of all, we will, if we want to check the pharmacokinetic parameter of a single drug, after giving a single dose, then we will check first its half-life. What the reported half-life is. If the half-life is 2 hours, then we will draw the samples from the animal or the human being at least 6.84 hours. Same case with the 3 hours. Then we will multiply with the 3. 3 means, then answer is 12.96 hours. 9.6 hours. I will discuss all these, how we are getting this point in our next class. Why we are using the word 4.32. Our next topic will be why we are using this factor. Thank you.